Okay, let's unpack this. We're diving into a really mind-bending question today. What if our entire universe, everything you see and experience, is actually just, well, a computer program?
It sounds like pure sci-fi, doesn't it? But it's a serious idea explored in, some pretty interesting scientific circles. And we're looking at it today through a very specific lens.
Right, the lens of a computer scientist.
Yeah.
Our source material is a paper by Jürgen Schmidhuber called A Computer Scientist's View of Life, the Universe, and Everything. And it really takes this concept and just runs with it.
Absolutely. So our mission today is basically to pull out the key ideas from this paper to help you get your head around this concept of a computable universe. What does it mean for things like, say, randomness or even life itself? And learning.
And can, looking at some classic philosophical puzzles from this, like computational viewpoint, actually make them simpler.
That's the claim. We might uncover some surprising stuff, maybe even trigger an aha moment or two for you.
Okay, so where do we start? The core premise.
Exactly. Let's begin there. The paper uses this helpful analogy, kind of a conceptual framework. Imagine a great programmer who wrote a program running on his big computer.
And just to be clear, the paper stresses this isn't about religion, right? It's purely a way to think about the idea.
Precisely. It's a tool to explore computable universes. The key assumptions are, well, first, that each universe evolves step by step, discrete time, think frame by frame.
Okay.
And second, that its state at any given moment can be described using a finite number of bits, like a huge digital snapshot. If a universe works like this, the paper calls it computable.
So basically, the only universes that can exist in this view are ones that can be computed.
That's the idea. Possible equals computable. And how are they computed? The paper brings in the concept of a universal Turing machine. That's the theoretical big computer.
Right, the ultimate flexible computer model.
Exactly. And different input programs fed into this machine produce different output sequences of bit strings. Each bit string is a snapshot of a universe at a specific time step.
And the first bit string in the sequence is the Big Bang.
Sort of, yeah. It's the initial state. Now, what's really neat is the choice of which universal Turing machine doesn't actually matter fundamentally.
Why is that?
It's because of something called the compiler theorem. Essentially, any program for one universal machine can be translated or compiled to run on any other universal machine and give the same output. The underlying computability is what counts, not the specific hardware, so to speak.
I think I follow. So the great programmer's machine.
Mm-hmm.
It might not just be running our universe's program.
That's a key implication the paper explores. If you have a universal machine, why run just one program? Maybe the big computer is running all possible programs, systematically computing all possible computable universes.
All of them. How would that even work?
Well, the paper mentions methods like dovetailing. You run a bit of program 1, then a bit of program 2, cycle through them all, or maybe even computing them in parallel if the big computer has those resources.
Wow. And that completely changes how you think about time, doesn't it?
Totally. Creatures inside a universe, like us maybe, we experience our local time. We have no idea how much computation time the big computer is spending on our universe versus others. The great programmer from the outside might not even perceive time in the same way we do, or at all.
Okay, so we've got this idea of universes being computed, potentially all of them. What about their nature? Like, are they orderly or are they just random chaos? Regularity versus randomness?
Right. This is where the paper introduces concepts from something called Kolmogorov complexity theory. It's a way to measure the randomness or complexity of a sequence.
How does it do that?
Basically, it asks, what's the shortest possible computer program that can generate the sequence? Let's say the sequence is the history of a universe up to now as a long string of bits. If the shortest program is much, much shorter than the bit string itself, that means there's a pattern, some underlying rule. The sequence is regular, compressible, not very random.
Like the digits of pi. There's a short formula, even though the digits look random.
Exactly. But if the shortest program is basically just print this exact long sequence, roughly the same length as the sequence itself, then it's irregular. It's incompressible. Essentially, it's random noise.
Okay, so regular means compressible, irregular means random.
You got it. Now here's the kicker, according to the paper. Statistically, the vast majority of all possible computable universes should be irregular, just random noise.
Wait, really? Why?
Think about it. There are way, way more possible long, random sequences of bits than there are short, elegant programs to generate patterns. If you just pick a random program, it's likely to produce something complex and seemingly patternless.
But hang on, that doesn't sound like our universe at all. Our universe seems incredibly regular, right? Stuff falls down, planets orbit. Laws seem consistent?
That's the puzzle. We seem to be living in one of the very few highly regular compressible universes. But we also perceive things that feel random, don't we?
Yeah, like the exact path of a single molecule in the air.
Yeah.
Or, famously, quantum mechanics. The outcome of a measurement seems random. It feels like noise on top of the regular laws.
Exactly. So how does the paper deal with this apparent contradiction? It argues that this perceived noise doesn't necessarily mean the whole universe isn't compressible overall.
How so?
Well, think about quantum mechanics. The fundamental law, like the Schrödinger equation describing how the wave function evolves, is computable by a short algorithm. It describes probabilities.
Right.
When the wave function collapses during a measurement, we get a specific outcome. That outcome adds information. It seems like noise to us. But crucially, this noise isn't completely random. It's constrained by the probabilities dictated by the regular computable law.
Ah, I see. So even with the random outcomes, the whole history up to now is still way more compressible than just pure noise, because the underlying laws provide structure.
Precisely. The short algorithm can describe the laws and probabilities efficiently. It might need more bits to specify a very unlikely outcome versus a likely one, but overall the description is still vastly shorter than the raw sequence of events.
Okay, that makes sense. The paper also gives reasons why it might look random to us inside the system, even if it isn't fundamentally.
Yes, two main points. First, something called the halting problem means it's generally impossible, even in principle, for us within the universe to find the absolute shortest program describing our reality. We find short laws, our physics, but they might not be the ultimate compression.
So our best description might still seem a bit noisy or incomplete compared to the true underlying program.
Potentially. And second, there are observational limits, like Heisenberg's uncertainty principle. The act of measuring disturbs the system. This makes perfect prediction from inside impossible.
But that difficulty for us doesn't mean the great programmer, viewing it from outside, couldn't predict it if they knew the full state in the algorithm.
Exactly. Our internal limitations don't necessarily imply fundamental randomness in the process itself. True randomness, in this view, would mean there's no short algorithm, even for the great programmer, computing those specific noisy outcomes.
So our inability to predict perfectly doesn't prove true randomness exists.
Correct. A simple algorithm could, theoretically, generate patterns across vast scales that look noisy locally, but are perfectly determined globally.
Okay, this next point you mentioned earlier, it sounds really counterintuitive. Computing all universes is somehow cheaper than computing just one specific one.
Yeah, get this. It sounds bizarre, but it's about information cost. The complexity of the description needed.
How does that work? Cheaper how?
Because the algorithm needed to systematically generate and run all possible programs on a universal Turing machine. Well, that master algorithm is actually very short and simple. It's like a basic instruction. Try everything.
Okay.
Whereas computing just one specific universe's history, especially if it includes all those specific instances of apparent noise we talked about, remember, most individual sequences are incompressible.
Yeah.
So the program to generate that specific noisy history would have to be incredibly long and complex, basically listing all the noise.
Ah, I see. The recipe for making everything is simple, but the recipe for making this exact, slightly messy thing is complicated.
You've got it. More is less in terms of the complexity of the initial instructions for the great programmer. A short program for everything versus potentially huge programs for specific complex outcomes.
And the paper says this naturally leads to something like the many worlds idea.
Kind of, yeah. It's not necessarily world splitting, but more that if you're running all possible programs, you'll inevitably have many programs that start similarly, maybe representing the same basic laws but with different sequences of noise or slightly different initial conditions.
So they'd look like the same universe for a while, then diverge.
Exactly. They become different branches, different universe evolutions, all computed in parallel by the big computer running everything. From an elegance perspective, the paper suggests this is simpler, just one short master program, than needing a complex program plus some kind of external randomness generator to pick just one noisy path.
Okay, so let's loop back to our universe. It seems regular, compressible by a short-ish algorithm so far. What does that tell us about how it's actually being run, or maybe its future?
This brings in ideas from algorithmic probability, like the universal prior or the Solomonoff-Levin distribution. It's a way to assign probabilities to sequences.
How does that work?
It assigns a higher probability to sequences that can be generated by shorter programs on a universal Turing machine. The idea is if you were randomly generating programs, you're more likely to hit a short one than a specific long one.
And there's a theorem related to this.
Yes, the coding theorem. It basically shows that the overall probability of observing a particular sequence is dominated by the probability contributions of its shortest possible programs. The simplest explanations carry the most weight, probabilistically.
So applying that to us, since our universe's history seems regular and could be described by a relatively short program.
The universal prior suggests that it is, probabilistically speaking, likely that it is being run by one of its shorter, simpler algorithms rather than some incredibly complex, specific one that just happens to look simple so far.
Okay, and the implication of that is?
Well, if it's run by a relatively simple algorithm, the paper suggests this might mean our future contains less than the maximum possible randomness. Maybe more predictability than we'd assume if it were truly random. There's a basis to hope for continued regularity.
Interesting. Okay, let's shift gears slightly. What about life and learning? How do those fit into this computable universe picture?
From this perspective, life isn't initially defined biologically, it's seen computationally. A living thing's existence is just a particular pattern, a substring, within the grand bit string history of its universe.
Just a pattern of bits.
Fundamentally, yes. And for one pattern, say you, to recognize another pattern, say me, as life within the same universe, the paper suggests there needs to be mutual algorithmic information between your life substrings and mine.
Meaning there's a short program that can kind of translate one pattern into the other. We share some underlying computational structure.
That's the gist. We can recognize each other because our patterns are related algorithmically. And crucially, we don't need to know or bit string patterns to function or interact.
Does the great programmer need to know what life is?
Not necessarily. In this model, complex patterns we call life might just emerge spontaneously in some of the computed universes as a natural consequence of certain algorithms running. The programmer doesn't have to design it intentionally.
Wow. The paper even mentions infinite recursion, like simulations within simulations.
Yeah, it touches on that. Could some computed universes become complex enough that entities within them develop the capacity to become great programmers themselves, running their own big computers and simulating their own sets of universes?
So we could be in a simulation run by someone who's in a simulation.
Potentially. And the paper even chickily suggests that if our universe has the right properties, you listening could theoretically aspire to be a great programmer creating your own simulated realities someday.
Mind blown. Okay, what about learning? Can creatures in these universes actually learn from the past to predict the future?
Here, the paper is initially quite pessimistic, generally speaking. Across the space of all possible computable universes, most of which are random noise, learning is impossible.
Why?
Because for any past history, a bit string, there are infinite ways it could continue. And in a random universe, most future continuations have no algorithmic connection to the past. Knowing the past gives you basically zero predictive power. The shortest program to compute the future isn't much shorter than just writing the future down.
So learning, using the past to do better in the future, that only works in specific kinds of universes.
Exactly. Learning is only possible in the rare, regular, compressible universes like ours seems to be. No learning without compressibility.
Makes sense. You need patterns to learn from.
Right. But just being regular isn't quite enough. A universe that's just beep, beep, beep forever is regular but too simple. It also needs to be complex enough to have interesting structures that a learner can actually identify and use.
And the paper describes how a learner might work.
It outlines a model, yeah. Imagine a learner program trying to get more reward over its limited lifespan. It uses basic trial and error methods, primitive learning algorithms, to change its behavior or policy.
How does it know if a change is good?
This is key. It uses what the paper calls the success story criterion. It doesn't just look at immediate reward. It evaluates a policy change based on whether it contributes to a long-term acceleration of reward over its entire history. It's learning how to learn by finding strategies that consistently improve things over time.
That sounds much more sophisticated. Okay, finally, how does this whole computational framework supposedly help with those big classic philosophical questions?
The argument is that by stepping outside, adopting this great programmer's computational viewpoint, some problems kind of dissolve or get reframed.
Like what? Give me an example.
Okay, take life after death. The paper suggests thinking about it not mystically, but technologically. If you could perfectly record someone's essential state, maybe their brain's complete information pattern.
Like uploading your consciousness.
Sort of. If you could capture that pattern, a bit string, and simulate its continued evolution in a rich enough virtual environment, then resurrection or continued existence is, in principle, possible within some computable future continuation of the universe. It becomes a question of information and computation, not spirits.
So possible in theory, even if we can't do it now.
That's the idea from this perspective. No fundamental computational reason it couldn't happen in some universe continuation.
What about things like the mind-body problem? Body and soul.
From the great programmer's view, all of that brain activity, philosophical debates, feelings of consciousness, they're all just incredibly complex, computable patterns, substrings in the universe's data stream. There's no need for the programmer to inject some extra non-computable soul or mind stuff. The complexity arises from the computation itself.
So the mystery is in the complexity of the pattern, not some separate substance.
That's the perspective offered. Even when we talk about things that seem impossible or paradoxical, like logical contradictions or concepts beyond computation.
Like Gödel's incompleteness, or time travel paradoxes.
Right. The paper argues that the process of us thinking and talking about these things, our brain activity represented as bit strings, is itself perfectly computable and consistent, even if the content of our thoughts touches on the seemingly impossible. Our thinking about the incomputable doesn't make our thinking process incomputable.
So the act of contemplating a paradox isn't itself a paradox in the code.
Exactly. The overall conclusion is that this higher-level computational view simplifies many of these classic philosophical tangles by reframing them as questions about the properties and patterns of computation itself.
Okay, wow. So we've journeyed through this idea of a computable universe, run perhaps as one of countless programs on some cosmic machine. We've touched on regularity, randomness, Kolmogorov complexity.
The weird economy of computing everything, how that might relate to many worlds, and what it all means for life, learning, and even those deep philosophical questions.
It definitely leaves you thinking. I mean, if our reality is fundamentally just information being processed, a sequence of bit strings, does that change how you, listening, feel about your own consciousness, your place in it all?
It's a profound question raised by taking this computer science perspective seriously. What is the nature of our apparently regular yet seemingly noisy reality?
Definitely food for thought. Thanks for joining us on this deep dive.